Mhm. Let's start learning quantum mechanics from scratch.
Sure, we'll build it step by step. At the foundation, quantum mechanics describes nature at very small scales. Think atoms, electrons, photons. Instead of definite paths, we get probabilities. Wave functions describe the likelihood of finding a particle somewhere. One key idea is the Schrödinger equation, which is like a rule book that tells us how these wave functions evolve. Does that sound like a good start, or would you like to dive into any specific aspect right away?
Can you give a relation between what you just told, probabilities, and the wave function evolve?
Absolutely. The wave function is like the core ingredient. It's a complex valued function that encodes all the information about a quantum system. Now, the probability of finding a particle at a particular position is the square of the wave function's magnitude at that point. When the wave function evolves, according to the Schrödinger equation, those probabilities shift and change over time. So, by watching how the wave function evolves, we're essentially tracking how the probabilities of different outcomes evolve too.
Can you tell me for a particle in a box how the rules of quantum mechanics work there, and do we need to satisfy all the postulates in order to arrive the solution to that problem?
Oh, the particle in a box is a classic. You imagine a particle trapped inside a one-dimensional box with infinitely high walls. Inside, the particle can move freely. At the walls, it's strictly confined. To solve it, yes, we use the postulates of quantum mechanics. The main ones you apply: first, the wave function must be zero at the walls. Second, you solve the time-independent Schrödinger equation to find allowed wave functions, sine waves inside the box, and discrete energy levels. So we don't need all postulates for this scenario, but the core ones, wave functions, boundary conditions, and the Schrödinger equation, are essential to get the solutions.
So why do we use boundary condition, and why time independent one?
We use boundary conditions because they tell us what the wave function must look like at the edges of the box. Since the particle can't exist outside, the wave function has to vanish at the walls. That restricts what forms the solutions can take. Only certain standing wave patterns fit. As for the time-independent Schrödinger equation, it's used to find stable energy states. These are the allowed energy levels. Once we have those, we can later add time dependence if needed, but these stationary states are a natural starting point.
What are the stationary states that you are talking about?
Stationary states are the solutions where the system's energy is fixed. In the particle in a box example, these states are the standing waves that fit perfectly between the walls. Each stationary state has a specific energy, and the wave function doesn't change its probability distribution over time. So if you measured the energy in one of these states, you'd always get the same result. They form the foundation for more complex quantum behavior.
Okay, how did the Planck scale related with the postulates of quantum physics?
The Planck scale is more like a fundamental limit where quantum mechanics and gravity both matter. Tiny lengths, huge energies. The postulates of quantum mechanics, like the uncertainty principle and the wave nature of particles, hold at all scales. But when you get down to the Planck length, space-time might become quantized itself. In other words, the postulates remain the backbone of quantum theory, but at the Planck scale, they hint we'll need a deeper theory, like quantum gravity, to fully connect everything.
Okay,
If anything else pops into your mind as we go along, just bring it up. We can dive deeper or switch gears anytime. It's all part of the fun.
let's talk about commutation relation.
Are the heart of quantum mechanics. Commutation relations tell us how two operators behave when you apply them in different orders. For example, the position and momentum operators famously don't commute. Their commutator is tied to the uncertainty principle. These relations basically define what can be measured precisely at the same time. So understanding commutators is like understanding the rules of the quantum playground. What's fundamentally possible and what's not.
So what you are suggesting about when these two operator position and momentum do not commute, how does that commutation related with the uncertainty principle? If they commute, meaning what?
When position and momentum don't commute, it means the order in which you measure them matters. Their commutator is proportional to the reduced Planck's constant. This leads directly to the uncertainty principle. You can't simultaneously know position and momentum with arbitrary precision. If they did commute, that would mean you could measure both perfectly at the same time, no uncertainty. But in quantum mechanics, that's not the case. The fact they don't commute is exactly why we have fundamental limits on how precisely we can know both.
But how did first they arrive at the conclusion, and how did they formulated the commutation relation?
It started with Heisenberg, Born, and Jordan developing matrix mechanics. They represented observables like position and momentum as matrices. When they multiplied these matrices, they realized that the order mattered. The difference between multiplying one way versus the other gave them a non-zero result. This difference became the commutator. They linked this to measurable quantities, and soon after, Heisenberg derived the uncertainty principle from that non-commutation. In essence, the commutation relations were discovered by exploring the mathematical structure of quantum operators, and from there, uncertainty emerged naturally.
Okay, why you talk about this matrix mechanic?
I brought it up because matrix mechanics was one of the first formulations of quantum mechanics. It's where these commutation ideas really took shape. In that framework, observables like position and momentum were literally represented as matrices. It's just one way to understand the underlying math behind the commutation relations. Of course, we also have the wave-based approach, but both tell the same story, just in different languages.
The commutation relation just simply tells us that we cannot measure two physical quantity at the same time. If we measure, we are violating the uncertainty principle.
Exactly. Commutation relations are the mathematical backbone of that principle. If two quantities like position and momentum don't commute, it's telling you that knowing one more precisely means you'll know the other less precisely. Measuring them both at the same time isn't forbidden, but the more exact you get about one, the fuzzier the other becomes. So it's not that you'd violate the principle, it's that nature itself imposes this fundamental limit. It's part of what makes quantum mechanics so unique.
So, when we think of computing with postulate of quantum mechanics, how did we go and how did we understand what actually it meaning for the computing sense?
When we think about computing in quantum mechanics, we move into quantum computing. The postulates become tools. The wave function is like the quantum state of a qubit. Operators, which used to represent measurements, become logic gates that change states. And those commutation relations, they shape what's possible in terms of operations. The uncertainty principle is reflected in the probabilistic outcomes of measurements. So we understand that quantum computing uses these postulates to manipulate information in ways classical computing can't, like superposition, entanglement, and speedups for certain tasks.
So, how do we frame that computing architecture, and what does it mean if we achieve that goal? How does it solve a hydrogen atom problem?
In a quantum computing architecture, you start by encoding information into qubits where states can be superposed. Quantum gates act like the operators in quantum mechanics, evolving these states. When we measure, we collapse the state probabilistically. Now, if we achieve powerful quantum computers, we can simulate quantum systems like the hydrogen atom directly. Instead of approximations, we could model the atom's energy states, interactions, or even complex molecules, revolutionizing how we solve problems in chemistry and physics. In short, it means simulating nature using nature's own rules.
Okay, what actually computing meaning here?
In this context, computing means processing information by manipulating quantum states. Instead of classical bits, just 0 or 1, you have qubits that can be in superpositions, both 0 and 1 at once. Computing here means using quantum operations like quantum gates to evolve those qubit states. You perform algorithms like factoring numbers, simulating molecules, or solving optimization problems by harnessing quantum principles. The meaning is that this lets us tackle problems in ways classical computers can't, faster, more efficiently, or even solving otherwise impossible tasks.
Okay, let's talk about Is every wave function in quantum physics uh, can be a wave actually?
It's a bit of a twist, right? The wave function isn't a wave in the classical sense. It's more like a mathematical tool that has wave-like properties. It can interfere and show patterns like waves do, but it's not a physical wave traveling through space. Instead, it encodes probabilities. When we say the wave function evolves, we mean it changes in a way that predicts probabilities of outcomes. So it's a wave of possibilities, not a physical wave in the usual sense.
Uh, while formulating the postulate of quantum mechanics, how
When the
that postulates help us to tackle every problem at a Planck scale.
The standard postulates of quantum mechanics work well at atomic scales, but at the Planck scale, where gravity and quantum effects collide, we actually suspect we need a deeper theory, like quantum gravity or string theory. The known postulates still guide us, wave functions, operators, and uncertainties still apply, but space and time themselves might become quantized. In short, the existing postulates help us frame the problem, but at the Planck scale, we need to expand them to unify quantum mechanics with gravity.
What are the one best application of quantum mechanics we see every day?
One of the most practical everyday applications is the semiconductor technology in all your electronics. Quantum mechanics explains how electrons behave in materials, allowing us to design transistors. Without that, no computers, no smartphones. So every time you pick up your phone or open your laptop, you're seeing quantum mechanics quietly at work. It's everywhere, just hidden inside the tech.
Mhm. Rules of
If you
quantum mechanics and semiconductor. Can you give more detailed explanation?
Absolutely. In semiconductors, quantum mechanics explained how electrons occupy discrete energy levels. These form bands. In a semiconductor, there's a band gap between the valence band, where electrons are bound, and the conduction band, where they can move freely. Quantum mechanics governs how electrons jump this gap when energy like heat or light is applied. Transistors, which are the building blocks of all modern electronics, use these principles to control electron flow, switching on and off current, storing information, or amplifying signals. So, quantum mechanics makes modern computing possible.
When two electron collide with each other, does it obey the quantum principle?
Yes, absolutely. At the quantum scale, when two electrons interact, whether through scattering or repulsion, they follow quantum principles. Their behavior is governed by wave functions and probabilities. The Pauli exclusion principle also plays a role, as electrons are fermions, meaning no two can occupy the exact same quantum state. So their interactions are calculated using quantum mechanical scattering theory, and everything, energy, momentum, and spin, obeys quantum laws.
Let's talk about spin. Spin play a very key role in every particles. Every particle in the universe can be described using just spin.
Spin is a fundamental quantum property, but it's not the particle literally spinning like a ball. It's intrinsic angular momentum. Every particle, electrons, protons, even photons, has a specific spin value. It's crucial in quantum mechanics because it defines how particles behave, like the Pauli exclusion principle for electrons. But spin alone doesn't fully describe a particle. We also need properties like mass, charge, and interactions. Spin is a key piece of the puzzle, but it's part of a bigger picture that describes each particle.
Okay, when can we describe two particle interaction using spin picture only?
Not entirely. Spin plays a key role, especially in things like magnetism or the Pauli exclusion principle, but interactions depend on more than spin. You also need to know the particles' charges, masses, their spatial wave functions, and the forces at play, like electromagnetic or nuclear forces. So spin is one part of the story, but to fully describe two particle interactions, you need the whole quantum picture, not spin alone.
Can you give a broader application of spin in modern physics and modern application in today's we are using?
Sure, in modern physics, spin underpins a lot. In MRI machines, we use nuclear spin to create detailed images of the body. In electronics, spintronics exploits electron spin to develop advanced memory and logic devices like magnetic hard drives or emerging technologies such as MRAM. In quantum computing, spin states of particles like electrons or atomic nuclei are candidates for qubits. So spin isn't just theoretical, it's shaping imaging, data storage, and the next generation of computing.
Can you give example of data storage part?
A great example is magnetic hard drives. In them, tiny regions of material store bits of data based on their magnetic orientation. That orientation is tied to electron spin. In more modern spintronics, technologies like MRAM, magnetoresistive random access memory, rely directly on spin. By controlling electron spin orientations, we store information more densely, with faster speeds and lower power use. In essence, spin states become the physical 0 and 1 of data.
So there must be a large number of tiny magnet because each tiny magnet store one spin data.
Exactly. In devices like hard drives, each bit is stored in a tiny magnetic domain, and modern drives have billions of these. Each domain's magnetization corresponds to spin orientations representing a 0 or 1. In spintronics or MRAM, we also control individual spin states. Scaling down to nanoscale magnets lets us store vast amounts of data. So, yes, the sheer number of these tiny magnetic regions is what makes large data storage possible.
Okay, so spin is actually a magnetic quantum number.
Yes, you can think of it that way. Spin is a quantum number that's deeply tied to intrinsic angular momentum. Because of that, particles with spin act like tiny magnets. For electrons, their spin is linked to a tiny magnetic dipole, which is why we get magnetic effects like we do. So spin doesn't just describe magnetism, but it is fundamentally connected to how particles can produce magnetic moments.
What about this magnetic moment part and intrinsic angular momentum part about the spin?
So, the intrinsic angular momentum part is what we call spin. It's an inherent property of particles, like electrons have spin 1/2. Now, because of this spin, a particle behaves as if it has a tiny magnetic dipole. This magnetic moment is basically how strong that tiny magnet is. In other words, spin gives rise to a magnetic moment, so particles with skin can interact with magnetic fields. That's what makes spin so important in both fundamental physics and practical applications.
What further we can discuss about origin of quantum mechanics?
Ah, that's a journey. It really kicked off when classical physics couldn't explain certain things, like black body radiation. In 1900, Max Planck proposed energy was quantized to explain it. Then in 1905, Einstein used quanta of light photons to explain the photoelectric effect. But the full framework came in the 1920s. Heisenberg, Schrödinger, Dirac, and others formalized it. They introduced wave functions, uncertainty, and quantized states, giving us the quantum mechanics we know today.
What do you mean by that quantized state?
When we say a state is quantized, we mean it can only take on certain discrete values, not a continuous range. For example, an electron in an atom can only have specific energy levels. It can jump between them, but it can't just have any energy. This is different from classical physics, where energies can vary smoothly. Quantization is one of the core ideas in quantum mechanics. It's why we get distinct energy levels, orbital states, and stable atoms.
Does that orbital state varies for a different quantum system.
Yes, it does. Different quantum systems have different orbital structures. In atoms, orbitals are shaped by the nucleus's electric field, giving us familiar shells, SPD, etc. But if you switch to something like a molecule, orbitals change because multiple nuclei shape them. In solids, you get bands instead of discrete orbitals due to so many atoms. Even exotic systems like quantum dots or potential wells have their own orbital patterns. So while the concept of orbitals is universal, the specific shape and energy of orbitals depend on the quantum system you're dealing with.
So that's a very beautiful line you are mentioning about the orbitals. Orbitals are shaped by the nucleus electric field.
I'm glad you like that. It's fascinating how the shape of orbitals, whether around a single nucleus or a complex molecule, is all driven by the underlying interactions. And quantum mechanics gives us these neat, discrete patterns, making the invisible world of atoms so rich and beautifully structured.
Can you give conclusion what we have discussed till now?
We started from scratch with quantum mechanics, talking about wave functions and probabilities. We saw how the Schrodinger equation gives us quantized states, like in a particle in a box, or orbitals around a nucleus. We explored commutation relations and how uncertainty arises. Spin entered the picture, explaining magnetism and data storage. We saw how quantized states vary across systems. Essentially, we traced how quantum mechanics gives us a discrete, rule-based universe, shaping everything from atoms to technology.
Okay, thank you.